Again, sorry. My name is Mikhail Goncharov. I'm from Russia, but I'm not a Russian hacker. I'm just a Russian deep learning developer, and I'm very glad to present here our work, which is quantification of epicardial adipose tissue in low dosity images. You can see epicardial adipose tissue in this picture. I will shortly call it epicardial fat. And the first question is, why do we need to quantify it? And the answer is that epicardial fat volume is an early marker of ischemic heart disease, which is the top cause of death globally. But unfortunately, clinicians do not use this marker primarily because it is estimated in CT, and manual estimation is very time consuming. So now assume that we have an algorithm for epicardial fat quantification, then we need some data on which to apply it. So therefore, I'd like to draw your attention to one very interesting source of data on which you can apply your medical image analysis algorithms, which is CT screening data. CT screening is a curing of CT images with the purpose of detecting some target pathology, for example, lung cancer, in a relatively large population. Therefore, the specifics of this data is that these are most often ultra-low dose CT images because it is bad to irradiate a large number of patients with a full dose. And you can see an example of low dose CT image in the right picture. So you can see that it is of relatively bad quality. So summing up, let's develop and apply an algorithm for epicardial fat quantification in low dose CT images from screening programs to early diagnose the patients who can potentially have ischemic heart disease. So now let me define what is epicardial fat more properly. In the left picture, you see the pericardium line, and in 3 dimensions, you can imagine the pericardium as a bag which contains the heart. And now epicardial fat is a fat deposit located within pericardium, as you can see in the right picture. And now we see that epicardial fat volume estimation. There are 2 questions. First is how to localize pericardium interior region in such a low quality image. And the second question is how to obtain a fat mask within pericardium from such noisy Hounsfield units. Previously, it was proposed, the 2-step method was proposed for epicardial fat volume estimation in full dose CT images. At the first step, the pericardium interior region is segmented using a convolutional neural network, and at the second step, CT image is filtered via a median filter, and then fat mask is obtained by thresholding the Hounsfield units. And this method showed excellent correlation of 97% between ground truth and predicted volumes in full dose CT images. So we treat this method as a gold standard for full dose CT images, and our experiments are aimed to adapt this approach to low dose CT images. For this purpose, we first collected a data set which contains about 400 low dose CT images and 76 full dose CT images. Then we asked 10 radiologists to annotate pericardiums in these images. And then we trained a UNet model for segmentation of pericardium anterior region. And we assess its quality in cross-validation, in stratified cross-validation on this united data set. And here we report the DICE scores separately for low-dose CT images and full-dose CT images. And as you see, surprisingly, the quality of pericardium anterior region segmentation in low-dose CT images is comparably similar to the quality in full-dose CT images, and moreover, it's comparable to inter-rater consistency. So now we have a model for segmentation of pericardium anterior region. The last step, but not least, is to obtain a fat mask from the inside the pericardium. So here you see 3 examples of 3 approaches of how to do it, and to the standard Hounsfield range within the pericardium region performs really bad. In the middle, you see that the median thresholding, which works well for full-dose CT images, also works imperfectly for low-dose CT images. And interestingly, in the most right picture, you see that a Gaussian filter applied to the input CT image followed by Hounsfield unit thresholding results in relatively better mask. So to verify this observation, we collected a data set which contains 57 patients. Each patient has both full dose and low dose CT image, and as the period of time between occurring these both images was not very large, we assume that volumes, epicardial fat volumes in full dose and low dose CT images coincide. So we did not annotate pericardiums in these images, and we used the trained network to predict pericardium anterior regions in both low dose and full dose CT images. And then we did the following. We calculated the ground truth epicardial fat volume for each patient in full dose CT image using the median thresholding as a gold standard for full dose CT images. And then we varied the thresholding parameters in low dose CT images in order to minimize the mean absolute error between the resulting volumes in low dose CT images and the calculated ground truth volumes in full dose CT images. So in these plots, you see the results of this calibration. You see that blue color means the low mean absolute error between the volumes calculated in low dose CT images and volumes calculated in full dose CT images. So you see that the Gaussian thresholding with the standard Hounsfield range performs better than other approaches. So we ended with this approach, and now we have a pipeline for predicting the epicardial fat volume in low dose image. We first apply our neural network, our UNet, and then apply Gaussian thresholding. So to finally assess the quality of this pipeline, we collected one more data set, which contains 25 patients with both full dose and low dose CT images. We asked radiologists to annotate pericardiums in full dose CTs And then we calculated the ground truth volumes in these full dose CT images based on these pericardium annotations and using the median thresholding as a gold standard in full dose CT images. And then we apply our pipeline in low dose CT images to predict the epicardial fat volumes. And then we report, the mean absolute errors between the predicted and ground truth volumes, as well as correlation coefficient between them and bias in milliliters. Okay, here we can compare the mean absolute error of our method with inter-rater mean absolute error. We see that the method's mean absolute error is higher. However, it's acceptable for applications. And also, it's worth noting that correlation coefficient of 96% is similar to the coefficient that was reported in previous works by other authors in full dose CT images. Okay, so to conclude, I'd like to mention that first we see that pericardium interior region segmentation quality in low dose CT images is surprisingly comparable to quality in full dose CTs. Second, the interesting insight is that Gaussian filter is more appropriate post-processing step than for low dose CT images than popular median filter. And finally, the final quality of our method in low dose CT images is higher than inter-rater variability of assessing epicardial fat volume, but it's still acceptable for applications because acceptable quality of the method is about 15 milliliters. So that's it. Thank you very much for attention. Please contact us if you have any questions, and I will be glad to answer all your questions right now. So thank you.
Thank you. I see that there is one question.
Yes, I
maybe I can read it if you want. So which dataset are used here? Would it also work for early detection of the asymptomatic patients?
Okay, it's a good question. We used a private data actually from the mentioned lung cancer existing CT screening program in Moscow. So this is private data, and these patients actually do not have symptoms of ischemic heart disease, but actually we found out a lot of patients with large epicardial fat volume, so they are at risk of having ischemic heart disease in the near future. I hope I answered your question.
Yeah, I hope so. It's not my question. Okay, but